Welcome to Exponential, a Nexus podcast where we talk about people, code, and capital. I am Daniel Glenn. Today I talk to Grigore Roșu, who is the founder and CEO at Pi Squared. We talk about the next layer of Web3 and the future of verifiable systems. Yeah, we're really excited about this conversation today. I think the first thing, a good starting point for our conversation is just to maybe you could introduce yourself and tell us how you got to where you are now.
I'm Grigore Roșu. I'm originally from Romania, and I came to the United States for PhD, like many others from Eastern Europe. And I finished my PhD in 2000 at the University of California, San Diego. Then I worked as a research scientist at NASA Ames in Silicon Valley for 2 years. And then in 2002, I moved to University of Illinois as a professor of computer science.
Nice.
And in 2010, I founded my first company, Runtime Verification. And in 2024, 1 year ago, I founded Pi Squared. And this is how we got here.
Wow. So how did you initially, what was the first draw to computer science? And then maybe how did that work? How did you also get attracted to sort of the concept of verification?
So first of all, computer science was not even a science back in Romania. It was just mathematics and applied mathematics. And computer science was applied mathematics of some sort. But I found it very interesting. I went to some programming competitions. I learned how to program by myself. I loved it. And then I got a chance to come to the United States to do my PhD with a very famous professor in mathematics and a field that we call formal methods and formal verification. And then I learned that was not pure mathematics. It was actually called computer science or part of computer science.
Yeah.
And that's how I ended up doing computer science, coming from mathematics and looking for something interesting to apply mathematical logic and reasoning to.
Right. And that led to verification. That's
yes,
yeah.
Formal verification and verification. Yes, which is all about proving rigorously that systems are correct, that they do what they are supposed to do, what they promise to do.
Okay. Yeah. And so how does that, looking at that problem, how does that lead you to founding Pi Squared?
So Pi Squared really is the sum of everything I've done in my career, starting with early on mathematics, then programming languages. Programming languages is my specialty. That's what I teach at the University of Illinois. Also distributed systems and concurrency. I think the idea started from runtime verification. Actually, Pi Squared spun off runtime verification. We got a team of 20 engineers from runtime verification, and we founded Pi Squared 1 year or so ago, 1 year and a half ago. So the idea came from using proofs as the ultimate attestations of correctness when you do verification, right? So if you ask me, why is something correct? I can wave hands forever, or I can give you a mathematical proof, which you can check automatically. And that mathematical proof is the best possible argument that we know as a species to argue for something, to be correct.
Right.
So that's how we, that's how we got to verification.
And so maybe I can ask this kind of in the spirit of, explaining or digging a little deeper into Pi Squared. When you have to kind of zoom out and explain to people or a general audience what problem Pi Square solves, like where do you start that explanation?
So there are different levels of approaching the problem that we have in Web3 today. There are several limitations. One of the most obvious limitation is scalability, right? So blockchains are slow. Decentralization comes at a cost in performance. So with Pi Squared, we address this problem first of scalability. We have a weak consensus protocol that makes things super fast, Web 2 level fast. Imagine almost like real-time settlement, real-time performance in Web 3. You have the same experience when you do transfers or trades in Web3 using the pi² stack as you have in Web2.
Okay.
Like you go in an exchange and you do a trade there, you see instantaneous results. Same with the pi² stack. So that's one dimension, performance. Another one is universality with respect to programming languages. If you look at many blockchains, they have a hardwired programming language or computational model. Could be a
Mhm.
virtual machine or a programming language. And you don't see that in the world of Web2. When you go and buy a computer, you go and buy a computer. You don't go and buy a Python computer or a
Right.
Java computer. That would be
Yeah.
ridiculous, right? You buy a computer and then you can run any programming languages you want on that computer. We bring the same.
Mm,
Actually, that's so pi². The name pi² comes from proof of proof.
mm,
Because we reduce any programming language, any computation, any programming language using a field in computer science, a well-established field called formal semantics, which allows us to reduce computation to mathematical proof.
mm.
And that's the first pi in pi².
Okay.
And then from that mathematical proof, we generate a cryptographic proof that attests for the correctness and for the integrity of the mathematical proof. So that's why it's pi². It's cryptographic proof or zero knowledge proof of mathematical proof. So, right, so that is the second dimension. So we bring universality with respect to programming languages. And third, we bring universality also with respect to proofs. So what counts as a proof that something is correct, is verifiable? And here we have this mechanism that inspired the name of the company, where we factor truth through mathematics.
Mm.
If you claim that something is true, then you should have a mathematical proof of it.
Yep.
And if you have the right framework, you can generate that mathematical proof automatically from the claim itself. If your
Mm.
claim is a computational claim that foo evaluates to 42, then you should be able to generate a mathematical proof if you have the right computational stack for your computational environment. And then once you have the mathematical proof, now you can generate a cryptographic proof.
Hmm.
Okay, so scalability, performance, that's one aspect. That is, and all of these are completely orthogonal, right? Second is universality with respect to programming languages. And third is a universal proof mechanism to provide ultimate correctness arguments to anything that claims to be true.
That it also sounds like that universal proof is automated. If you're, like you said, if you're using the
Yes,
right stack or the right tooling, then
yes,
that becomes sort of de
yes.
facto
Because
proof.
it would be unmanageable
Right.
to write proofs by
Every,
hand,
yep.
mathematical proofs by hand. You want to generate them automatically.
Yeah. So I was reading something on the pi² website, which I just wanted to ask you about because
Mhm.
it sounded really interesting to me. So FastSet is one of the products that you are working
Yes,
on, and it says FastSet is
protocol.
not. What's that?
It's a
Protocol.
protocol, the
Okay.
consensus protocol. Yeah.
Yeah.
Mhm.
So FastSet is the consensus protocol, and it's what's from the site. It says FastSet is not another blockchain. It's infrastructure for thousands of future chains, apps, and agents to settle claims quickly, verifiability, and in parallel without bottlenecks of traditional consensus-based systems. So when I
Yes.
was reading that, the reason I wanted to kind of bring that up is it sounds like what you're talking about is almost a kind of a post blockchain world, or maybe
Yes.
borrowing conceptually from what we see with blockchains, um, and the sense of you know that consensus mechanism that we're becoming more and more familiar with. But then what it sounds like here is kind of now the next step is improving on that consensus
Yes.
so that it's
Yes.
faster and you can kind of get
Hmm.
to that scalability that you're talking about and all those other
Exactly.
features.
Exactly.
So
Exactly.
what do you think about that idea that if someone were to say, oh, this sounds, like post blockchain, or maybe the next, generation of what
Yeah.
follows blockchain, what do you think about that?
Well, so I'm living it. So we are convinced that blockchains are not the final answer to the
Mm,
Web3 quest. We all agree with the values of Web3, that people should own their own assets. Nobody should stay between them and their assets. But now the question is how we accomplish that. And when it gets to how, we humans are very ingenious. We come up with all kinds of solutions that are better and better and better. And blockchains are just one solution that allows us to securely, verifiably, in a decentralized, censorship free manner, right, we have access to our assets and we can transfer them around.
Mm.
But again, let's keep in mind that we don't care that much how things work. Same
Mm.
like when you drive a car, you can drive a car, you can switch from a gasoline to an electric car very quickly, right? It's not like a massive experience. You don't have to relearn how to drive or anything like that. We already know how to do that. Same in Web3. Blockchains give us a good solution. They had a very good run until now. But we believe that we have to transcend blockchains. We have to
Mm.
go to the next level. And the main reason for doing so is the scalability bottleneck, which is not avoidable, which is not solvable by just incremental improvements. We need a paradigm shift. Um, and I can go deep into that. Again, distributed systems and concurrency is something I teach, but at a very high level, there is
Mm.
this concept called strong consistency,
Mm.
where when you have a distributed system with lots of nodes, strong consistency means that all the nodes at any given moment in time, if you freeze the entire universe,
Mhm.
they all see exactly the same state. They replicate the same state. Everybody has exactly the same state
Mm.
internally. This is called strong consistency. They are strongly consistent. And this is what blockchains do. At each block, all the validators, all the nodes will have exactly the same state. Okay? And it is probably not very hard to realize, even if you are not an expert in distributed systems, that this requires a lot of communication and synchronization between the nodes to make sure that we all have exactly the same state. There is another concept in distributed system which was invented actually not too long ago, only like 10 years or so ago, after
Mm.
Bitcoin, definitely, called strong eventual consistency,
Mm.
which means intuitively that the nodes are allowed to have different states at different moments in time. So if you freeze the entire universe and look into their states, they are different.
Mm.
However, eventually, when all the transactions are cleared, everybody will have the same state.
Mm.
Okay, so, and the reason they have different states, intermediate states, is because they process the transactions in different orders. They may receive the transactions in different orders, and they do not queue them. They do not wait until there is a total order on the transactions. They just process the transactions as they come in parallel. And that's what actually gives the performance. Now it is as fast as the internet because
Mm.
each validator receives all the transactions, processes them in the order they receive them. And now there are mathematical guarantees that the order doesn't matter. Eventually they get the same things. If certain properties hold and FastSet enforces those properties, it's called weak independence between different transactions. For example, payments satisfy that property, voting, auctions, escrows. There are lots of applications. More than 90% actually of all the transactions on Ethereum
Mm.
are weakly independent, which means that they do not require a total order. They do not require strong consistency.
Huh.
Okay? And then we said, then why pay the price? Why pay the price of strong consistency or total order on
Which is
all the...
speed, right? In this case, the price is
Exactly.
speed.
When
Yeah.
we can just simply process everything in parallel, massively parallel.
Right.
And the catch here is that sometimes you do need a total order.
Mm.
For example, Uniswap, right? Where you swap one token for another. The order matters because that establishes the price of
Oh,
the
right.
asset.
Right.
Okay? Well, in those cases, in these isolated cases, you can have smart contracts whose job is to execute transactions in order, to find an order, sequencing, and so on. But you
Mm.
don't have to sequence the entire universe
Right.
because one application requires sequencing.
Just for the order book, right? Yeah. Yeah.
Exactly,
Yeah. Yeah.
exactly. So now what we did, we said, let's actually step back and allow the world, the universe to be completely parallel as it is actually in real life as
Mm.
well. Everything happens in parallel. And whenever we need sequentiality, we can do it. We know how to do it. We just have to write a program that says, this is the order in which you execute them, as opposed to taking the order for granted because the entire universe is ordered. Probably that was a long explanation to something that should have been simpler, but the
No.
bottom line
Yeah.
is that FastSet, think of FastSet as a massively parallel. We call this embarrassingly parallel, and it's
Huh.
embarrassingly parallel protocol, where every single transaction is processed, it is finalized and settled in parallel with all the others. And the validators don't even need to talk to each other. So we currently reached, if you go to our website, fastset.xyz,
Mhm.
and play with the protocol, you will see real time. You'll have a real time experience. You can transfer tokens, digital assets in real time. Actually, Zoom or Riverside will be
Yeah.
actually slower
Oh,
than
wow.
so the transaction will happen before you can see it actually on the screen.
Yeah.
So it's super fast, and so it's more than 100,000 TPS currently, and less than 100 milliseconds finality. And each transaction is finalized completely independently from the others. No blocks. Nobody has to stay in line for
Right.
nobody else.
Yeah, that's what I was gonna ask. Is there still that convention or that sense of having like a finalized block?
No, no.
No.
Each transaction is finalized completely independently of the
And
others. So transaction which is sent later can be finalized before the other one if the internet, connections are in a certain way.
and is there still the same kind of audibility or
Yes,
transparency that you see on a blockchain? So you'd still be able
exactly.
to go back and look at oh, this transaction happened here and this is the sender
Yes.
receiver kind of thing.
Yes, you can see all the transactions. It all feels and looks like a blockchain. I can share my screen. I don't know if we can do that in a podcast. I can share and show you how it is. It's actually literally, literally. But I encourage
Yeah.
the audience to go to
Yeah.
fastset.xyz and just
Yeah.
play with it.
Play with it. Check it out.
You have an explorer, a blockchain. It's not a blockchain. It's a set.
Right.
We call it a
Right.
set. A set explorer. You can go through all the transactions, verify everything. Everything is verifiable. Everything is correct, secure. Same like on a blockchain. Everything is signed with a private key, and you have exactly the same experience as a user. It's just what happens under the hood that is
Right.
completely different. Like from gasoline cars to electric cars,
Oh,
under the
okay.
hood is all the difference,
Yep.
and the speed.
Awesome. That's a great analogy from gasoline cars to electric cars. Yeah,
Yes.
it's good. And I'm kind of wondering if we could zoom out a little bit. And you
Mhm.
talked about this at the beginning. And this is kind of what, you know, I think where Nexus and Pi Squared kind of share the same vision for the future. And that vision is based on verifiability. Of course, we're
Yes.
working on different problems and kind of different technologies to create that future. But I'm kind of, when you zoom out and look at this as a whole, especially from your perspective as someone who studied mathematics and then computer science and teaches computer science, how do you think about that sort of big picture vision of verifiability and what does that look like, in the future?
So when we talk about verifiability, we implicitly talk about a proof. Because without a proof, I cannot verify much. Sometimes the proof may be just re-executing the whole thing. The whole thing can be the proof. Yes, sometimes happens, but most often than not, we have more concise proofs for certain things that
Mm,
are claimed to be true. These things are executions of programs. And now there is huge progress on the zero knowledge and cryptography front these days. We have very powerful zero knowledge circuits that essentially can compress. We can think simplistically, of course, of zero
mm,
knowledge proofs as massive compressors. Right, so I can compress an execution of a program that can have millions of steps or billions of steps into 256 bits or
mm,
1 kilobyte of size. So the whole thing is compressed in a very smart way. And it's not a perfect compression because these are probabilistic arguments. There is a very, very low probability that the proof can be wrong, or something might happen, in the universe,
right,
with some alpha particles that can go through the circuit, and some errors of some kind can appear. But essentially, these cryptographic proofs, and Nexus does an amazing job at that. These cryptographic zero knowledge proofs, they are proofs. They attest for the correctness of the
mhm,
of the program execution. So now you don't have to re-execute. You can just simply settle the claim, the computational claim.
right,
Okay, so that's what Nexus does. That's also what Pi Squared does. We also do the same thing. We have a different way to get the zero knowledge proofs. We go through a mathematical proof. So we execute the program using a formal semantics and get a mathematical proof. And then at the same time, from the mathematical proof, we generate cryptographic proof, a zero-knowledge proof that the mathematical proof is correct. And then there are several other companies, Risk Zero, Succinct, they all do similar things.
Yep.
They have, because again, there was an explosion of talent and ideas and creativity in this field in the last few years. Now, once I have the claim and the proof, we can talk about verifiability. And you can verify also without zero-knowledge proofs. I don't want people to think that you need zero-knowledge proofs to have verifiability. No, you can have verifiability. Also, the whole claim itself can be considered the proof. And now you can re-verify the claim by going step by step through the claim, re-executing the claim. That's what Ethereum does, for example, re-executes the claim, re-executes the program. But that's a long proof and an expensive proof, right? The cryptographic proofs are nice that you pay the cost once to get a massive compression, and then you can check them very efficiently. Okay, and now think of FastSet as the place where now you can take all these claims with their proofs to be verified and settled once and for all, permanently. All right? So, in fact, even the payments, if you play with the wallet, they also claims of payments, and the signature is the proof. It's same like a zero-knowledge proof. And now once you have that, you can settle the claim and you can see the transfers being made from one place to another. But this can be arbitrarily complex computations. So now to get back to the question of verifiability and how we see verifiability. So first of all, Web3 without verifiability doesn't exist. That's the whole point of Web3. And that's why we want to own assets and to be able, to have a peer-to-peer transfer network, right, for our assets. And without verifiability, why can you trust anything, right? We cannot trust Google Cloud. I mean, we do on a regular basis.
Yeah.
But at some point, we know that if Google wants your, pictures to be changed, they can change them, and there is nothing you can do about it, right? They can put somebody else in your picture, and there is nothing you can do about it. You cannot even verify it. It's just you get what you see. But with verifiability, and especially with cryptographic attestations and proofs, nobody can cheat, nobody can change what's yours. And that's part of the ethos of Web3. And
Right. The whole
definitely
idea of
want that.
digital property rights and kind of being able to verify
Precisely.
your
And
own
with
property.
FastSet, we allow a network of verifiers for any claim. So any claim that is made is verified by a network of verifiers, and they give each a thumbs up to the claim. And once you get a quorum of such verifications, now the claim can be settled. There is another layer of verification, but we call that validation, much simpler validation, which only validates that the verifiers were legit.
Okay.
And they verified correctly the claim. It's like verifying the verifier
Yeah,
or
right.
validating the verifier.
Yeah.
And now once you validate the verifiers, now you can settle it. And
I
once it's
see.
settled, then it's permanent. You cannot change
Okay.
it anymore. And nobody can argue that it didn't happen. So
And you mentioned that, we're kind of seeing, and it sounds like, I mean, I think from our vantage point at Nexus and your vantage point at Pi Squared, and I'm sure probably talking to your students too, it seems like there is this idea of zero knowledge cryptography and just verifiability in general is kind of having this moment, and there's a lot of attention being paid to it and a lot of talent kind of moving to the space and a lot of interesting companies and products being developed like super fast. And I'm kind of curious, from your perspective, why do you think that's all happening now? Like what has either changed, or what's the sort of what's the driving force there?
yes, I think it's a mixture of incentives and technology. So first of all, there is a big incentive, economical incentive for zero knowledge proofs,
Hmm.
because instead of having a million nodes re-execute the program and each of them paying the cost, the energy of re-executing the program, now you can have it executed only once and the proof is generated and everybody else will verify the proof. So it's like a million, almost not a million, but many orders of magnitude less energy consumed for that. And actually, it can also be faster. Many people, there is a common misconception that zero knowledge proofs are slow. Actually, end to end, they are not, because you can have a super powerful machine, a supercomputer, to generate the zero knowledge proof, and then you can have simple computers, even phones, verify the zero knowledge proof instantaneously. So
Hmm.
end to end, you actually spend less time, less energy. Okay, so there are economic incentives for zero knowledge proofs. Then there is there are lots of scientific results that converged um, recently that made all this advancement of zero knowledge technology possible.
Hmm.
Lots of cryptographic primitives, algorithms, circuits, tricks,
Right.
how to make things work fast. And all this together made it possible to generate zero knowledge proofs, in minutes instead of days, like it used to be. And then from minutes with parallel powerful hardware GPUs, we got to seconds. Even I believe now we can even prove ZK prove the Ethereum blocks, right,
Oh,
in
yeah.
10, 15 seconds, right?
Mhm.
So you can keep up. We can keep up with. I think Succinct did that. So you
Yep.
can keep up with Ethereum, which is wonderful. That means what I just said. We can have a powerful computer generate the zero knowledge proofs,
Right.
and then all the validators can be very simple machines, only verifying ZK proofs. Well, I'm simplifying things.
Yeah.
Okay. You also have to settle then the state, modify the state. The state is the big killer. The data,
Mm.
storage, and all
Right.
those are still there. ZK cannot save us from them. Also, consensus. Consensus cannot be solved by ZK. So ZK zero knowledge solves one important problem. Think of it. One way I like to tell my students, to think of ZK is like think that God signs the program executions or the claims that you make. If it's true, it's signed by God immediately, right?
Mhm.
And now you can recognize the signature of God right away. I know it's a bit too far, but the idea is that you don't need to worry about the truth, the validity of a statement once it has this magic signature.
Okay.
You just check the signature and you know it's true. And that's nice because you don't need the power, the energy to recheck a complicated artifact. And sometimes you cannot have access. Some information is private
Mm.
in the actual claim that is being made. And then the zero knowledge proof hides that information. And finally, I think zero knowledge proofs are just very interesting. If you are an
Yep.
intellectual and you start looking at it, the first, actually, even myself, when I first looked at zero knowledge proofs, I said, no, that's impossible. It cannot be done.
Hmm.
And then I understood the assumptions a bit better, the guarantees a bit better. And I said, actually, it is possible. And then, wow, this is super interesting. And
Mm.
then I was hooked.
Yeah. So when we think about, it does seem like there's a lot of attention right now being paid on the technical problems of zero knowledge, and taking a lot of that research you mentioned and a lot of these recent breakthroughs, um, from academia and elsewhere, and putting them into the industry context and making them more accessible to more people. But I guess my question is, what other conditions have to be in place, or what other are there other limitations in your mind for, before we can kind of hit this mass adoption of, verifiable computation, or zero knowledge proofs? Like, are there other things that have to happen, or is it merely a technical problem?
I thought for a long time that it's mainly a technical problem because that was my comfort zone.
Yeah.
And I wanted to believe that my comfort zone is the zone. That's where I should stay, and that's what we should do.
Hmm.
We should work on this very hard problem. But then, as soon as we had our first circuits and our first proofs, and tried to deploy them to actually settle verifiable claims on blockchains, even on the fastest of them, we realized that they were so slow. Um,
Hmm.
I mean, I used blockchains for a long time. I started, not very long. about 10 years or so. But mostly doing transfers, from centralized exchanges to, to my hardware wallet, or,
Right.
from one account to another, or sometimes swapping. And I was forgiving because I did it like very rarely. It was not something I do every day.
Yeah.
So I was very forgiving. But as soon as we started using and deploying proofs, um, on blockchains, even the fastest of them were very slow. And then we had this revelation that, wait a minute, even if a blockchain does 10,000 transactions per second, and there are some that can do that. Mega ETH, for example, can do 20,000 transactions per second. They can sustain 20,000 transactions per second. Some claim a lot, but I'm not sure. Everybody, all of them can be trusted, or all of them measure properly, right? The number of transactions. But even if let's exaggerate. Suppose that you can do 1,000,000
Mm.
transactions per second on a blockchain. Okay, that's still not enough. If we truly believe that Web3 is here to stay, and all our digital assets will be, protected by cryptography on Web3, and if AI agents, which are here, it's not a future, they are here
Yeah.
already, also use Web3 for payments, micropayments, to communicate with each other, then we get to a point where very, very quickly we'll have more than even 10 million transactions per
Mm.
second. They need to happen.
Yeah.
You simply cannot sustain all those on a totally ordered chain. Imagine that you have like a football stadium, right? And you want to go from one end to the other. But suppose that there are 1,000,000 people, not only one, or a large number of people, and you have a narrow door in the middle of the field, and everybody has to go through that door.
Yeah.
Okay, and there's only one person at a time that can pass. No matter what you do, no matter how well organized you are, no matter how good, you know, how well trained these people are to run fast and
Yeah.
and to interleave, it will be slow,
Yeah.
right? As opposed to just going in parallel. If everybody goes in parallel on the other side, and by the way, nature doesn't do that. Nature is parallel, right? If I
Right.
look at that tree in front of me, the leaves, all of them move at the same time in parallel in the wind. They don't care
Mhm.
of a total order.
Right.
So that was my revelation. I realized that, hey, this cannot really become mainstream and widely accepted if it stays as is.
Mm.
And then I thought that maybe actually Web3 was not meant to be, or at least not meant to be as broadly, accepted or widespread, and accepted by masses as I initially thought. Until we started looking into the very recent research last few years, and we realized that there are several scientists, um, who looked deeply into how to avoid the bottlenecks, the problems of strong consistency. And the idea appeared like 10 years ago, strong eventual consistency, but the first practical paper was about 5 years ago,
Mhm.
published, showing that, wait a minute, you do not need a total order to avoid double spending. Satoshi Nakamoto thought, and not only him, but everybody back then, they thought that the only way to avoid double spending is to have a total order, to have a ledger,
Mhm.
totally ordered list of transactions. And then, of course, you cannot have double spending because either one or the other transaction will need to be first. Um, and that's what the belief was until 5 years ago or so, when the first protocols were published showing that, nope, you don't need a total order. You can avoid double spending differently.
Hmm.
And that's the magic of it. And to me, that was the aha moment. I said, yes, that's what we need. And yes, Web3 is legit. Web3 is great. It's just blockchains which have a limitation
Just
that we
blockchains
have
are
to
the
fix.
problem. Yeah. Yeah, that's
Exactly.
interesting too. The way you explain it, it sounds like the founder and CEO of Nexus, Daniel Moran. He's said this before too. Like the place you want to be is working in problems, working on solutions to problems that feel inevitable. Or the solution feels inevitable. And when you think about that stadium example and our need for, right now transaction speed can't even kind of keep up, and we're just humans doing transactions. And like once you add that element of AI agents, like you were saying, and
Yeah.
and more people start adopting these systems, then it does feel inevitable that something has to give there.
Yes. Yes.
Okay, so last question I have for you today. If you were to look ahead, and you can take this looking ahead can be kind of broadly interpreted here, like 5 years, 10 years out. But what do you see? And we can kind of limit this to specifically to verifiability because that's what we've been talking about. But what do you see, and what kind of gets you excited, and or like what do you kind of feel like are the big unanswered questions that we still have to kind of tackle before we can move things forward?
So I think at a conceptual level, we kind of finally understood what needs to be done. But there are still lots of engineering constraints and limitations that we need to overcome. For example, we really want to allow all programming languages in Web3. Smart contracts should be written in Java, C, um, Python, any programming language. Why Solidity? Why EVM? Why Move? By the way, Move is a great language, but still just one language. So why not? Why not allow any programming language, and then automatically get proofs from all of them, which are correct by construction. So proofs which come directly from the mathematical definitions of the programming languages.
Hmm.
And we know how to do that. Actually, we knew how to do that for many years. It's just that it's all very slow. We need to improve performance. We need to make things a lot faster. Yeah, the problem of settlement. Now we have algorithms that are uncapped. So these algorithms, the massively parallel settlement algorithms, once you have verified claims to settle them in parallel, that can be done. And theoretically, there is no limit,
Hmm.
no cap, no max TPS. Okay, so it's unlimited. But to implement really fast networks, you need to engineer them well. And we run into issues of, even speed of light. We cannot get as
Hmm.
fast enough, right, the
Yeah.
information to other validator nodes. It doesn't matter if they answer immediately, if they know immediately what to do, and there is no more communication, it's just one message back and forth. You cannot go smaller than back and forth, one message back and forth. You have to send your message, your claim to the validator, and you have to get the approval, right? So a round trip message, but a round trip message takes 100 milliseconds
Hmm.
currently on Earth. Maybe fiber networks will make it faster. Right. So I see lots of engineering challenges, but to be honest, at this point, I do not see any deep conceptual hurdles
Hmm.
that stay in our way. I think, and engineering problems, those are solvable. I think we'll solve all of those, and we'll have Web3. Web3 will disappear actually as a concept because it's there. It's ingrained in everything we do. We'll not have to say this is Web3 anymore.
It
Same
becomes
like,
the background for everything, right? Like,
well,
yeah,
for everything,
yeah,
yes, because it's just natural for us to own our own assets. I cannot imagine a world where we don't, and we know how to do it, and it will
yep.
happen. It's happening.
And
Yeah.
be able to move them at the speed of taking
Yes.
action, I
Right.
guess. Yeah,
Exactly. Exactly. I mean, Bitcoin has become a store of value, right? Because first of all, the value is very high,
yeah,
and also it's very slow, right? So
yeah,
it's a good narrative for a store of value. But now imagine that you can do all the transfers instantaneously, right? Then you can imagine an economy that is fully decentralized and super fast. Actually, bank transfers are very slow.
yeah,
Not even clear why they are so slow.
yeah, yeah,
Email is slow, right? We can move a lot faster than many of these. You know,
yeah. Well,
even
I
many.
appreciate that perspective that a lot of the mathematical or the conceptual problems have been are at a point of readiness where we can take action, and then now it comes down to engineering challenges, which, like you said, are solvable. So that paints a positive picture for our future, I guess, if you believe in the sort of the reasons for these technologies in the first place. So
And we can also ask help from AI these days,
yeah,
right? AI is great at finding solutions to repetitive and boring problems. Like
yeah,
getting the mathematical proofs.
Right.
So AI can help us get mathematical proofs, and then we verify them. We can
Hmm.
have AI generate not only the programs, but also the proofs why the programs are correct. And then we humans only verify them,
Hmm.
right? So there are many interesting
Yeah,
aspects.
definitely. Well, hey, I appreciate your time today. That was a great conversation, and I appreciate, and I'm sure our listeners will appreciate learning more about pi squared and what you all are up to there. And we'll check out. We should all go check out FastSet and play with that transaction record and see what that's like. And thanks again for your time.
Thank you, Daniel. Great show. Thank you.
Yep. Thank you for listening to this episode of Exponential. We'll be back next week with another show featuring people, code, and capital. Please like, review, and share Exponential wherever you listen to your podcasts. And be sure to visit app.nexus.xyz to see what we are building.